Hello and welcome back to Lesson 8, More Advanced Limits. So, for today we're going to be talking about the idea of local agreement and the limit of the composition of functions. So, two functions f of x and g of x are said to be in local agreement at x naught if around x naught but not at an x naught, f of x is equal to g of x. So, what does this mean? Well, we'll use an example. Recall two functions that you may have seen in pre-calculus. Let's say this is function f and this is function g. We know that f of x is equal to this, and for all x in the domain of f, this is equal to x plus 4, which is equal to our g of x. So while f of x is not equal to g of x for all x that belongs to real numbers, if x is not equal to 3, then fx is actually equal to g of x, meaning that if we take the concept of locality, which is building a delta neighborhood around our x naught, but not exactly, right? It's punctured, it doesn't include the x naught. Locally, at x equals 3, the two functions, we say they agree, right? F is equal to g. So we can say that a punctured delta neighborhood around x naught equals 3, the functions f and g are in local agreement. In other words, this is true if there exists a delta greater than 0, such that the distance between x and x naught is not equal to 0, so it's greater than 0 and less than delta. That implies that f of x is equal to g of x. Now notice that the limits at x naught of both f and g appear to be the same. This is going to help us because we're going to try to prove that indeed they are. This is the theorem, the local agreement of limits. If the limit as x approaches x naught of f of x is equal to L, and locally at x naught f of x is equal to g of x, then the limit as x approaches x naught of f of x is equal to the limit of g of x as x approaches x naught, which is equal to L. So proof. Suppose our hypothesis, and we'll fix epsilon to be greater than 0. This whole monstrosity, which is if the limit is a real number, positive infinity or negative infinity, is implied by this, but we have to recall that locally at x naught, f of x is equal to g of x by hypothesis. And that implies this, right? Locally at x naught. Remember, this is our definition of the limit when we supposed this. And that implies, because f of x is equal to g of x, that. So that's our proof. Not too difficult, pretty simple. So let's evaluate the limit as x approaches 2 of the following function. So here, by the local agreement theorem, so since the function right here agrees with the function right here, locally at x equals 2, we can write x not equal to 2. Local agreement theorem, the limit as x approaches 2 of x plus 3 times x minus 4. Or, as you may call it, we can cancel it out, but we have to write x is not equal to 2. Remember, I talked about this in some of my earlier videos, answers -10, when I said that you can kind of cancel it out. This is what I meant. So how do we use the local agreement theorem for piecewise functions? Well, let's let g of x to be the following piecewise function. Let's evaluate the limit as x approaches 2 of g of x. Recall that locally at x naught equals 2, g of x is equal to x squared plus 1. Since x equals 2 is not a value considered, remember that locally at x naught, at g of x is x squared plus 1. So the limit as x approaches 2 of g of x by local agreement theorem is the limit as x approaches 2 of x squared plus 1, which is equal to 5. In general, for more complicated piecewise functions, one-sided limits are necessary. So in this case, we have an easy x is equal to 2, x is not equal to 2. If we have intervals, or more complicated intervals, we always have intervals, then we're going to have to start using one-sided limits, and we'll get onto that later. Now let's recall what a composition of a function is. The composition of f and g of x is f of g of x. Remember, we denote it with a little o because o is like f of g, or fog. If f of x is equal to x to the 7 and g of x is equal to x plus 5, find the composition of f and g. Well, their composition we'll call as f of g of x, which is f of x plus 5, and plugging that into our f of x, into our x to the 7, x plus 5 to the 7 is what we get. So hopefully you still remember how to do that, because it is going to come up right now. So the limit of composition of functions. If the limit as x approaches x naught of f of x is equal to L naught, and the limit as x approaches x1 of g of x is equal to x naught, and locally at x naught, g of x is not equal to x naught, we have a little exception here, but we probably won't have to consider that, then the limit as x approaches x1 of the composition of f and g, which is the limit as x approaches x1 of f of g of x, which is the limit as x approaches x1 of g of x of f of x, is equal to the limit of f of x as x approaches x naught, which is equal to L naught. Here's our proof. We're going to fix epsilon b greater than 0, and we'll, of course, I don't write this, it's implicit, assume our hypothesis. Then the following, which we get from the first limit, is true if 0 is less than the absolute value of g of x minus x naught, less than our delta 1. This is kind of, we look at our, this is kind of like our x, and this is our x naught, except here x is our g of x, so x, remember the definition of a limit, it's something like this. And this is implied, we can consider it in its own limit, because remember g of x is not equal to x naught, so we can write 0 is less than, and this is implied by right here on the left, is implied by what's on the right, because by our definition of our limit here, if we just let this delta 1 be like an epsilon, let's say a positive number, positive real, then of course 0 less than x minus x1 less than delta 2 by our other limit right here, and we're done. That's our proof. Again, these proofs are not super complicated, and here are 3 examples. So evaluate the limit as x approaches x, as x approaches minus 2 of x plus 1 to the power of 10. Now here's where composition of functions comes into play. This is the limit as x approaches negative 2 of the composition of which 2 functions, x to the 10 and x plus 1. Because remember, what is this composition? Was x plus 1 to the 10. And this is, how do we apply the theorem? Well, it's the limit of as x approaches the limit as x approaches minus 2, x plus 1. So remember, we take the rightmost function right here, the right function, we put it here, the limit as x approaches the same exact number here of the right function, and all of that of the left function. So that's equal to, what's this limit? Well, this limit is easy to compute, it's just minus 1. The limit as x approaches minus 1 of x to the 10, which is 1. Our second example, again, very simple. We have to figure out our composition. In this case, this is our composition, and we can write this as the limit as x approaches the limit of x minus 5 as x approaches 5, which is 0. So it's the limit as x approaches 0 of x cubed, which is 0. And finally, we're asked to evaluate this limit. Well, you should notice, if we set this to be u is equal to x plus 2, and the u to 13, we have our 2 functions. So the composition is x to the 13 composed with x plus 2. And this is equal to the limit as x approaches the limit as x approaches 4 of x plus 2 of x to 13. I think talking, you really aren't going to understand it. It's better if I show you. And this is, of course, the limit of x approaches 6 of x to the 13, which is 6 to the 13. So hopefully this helped you out. And it's another very important tool that's very helpful as we start to get onto more advanced and complicated limits. Thanks for watching.